Hello, everybody. Welcome back to Markov Processes. I have a little bit of a cold today, so my voice is going to be even more nasal than usual. Sorry about that, but I got to take advantage of any time I can find to film one of these videos, so I'm going to persevere. And yeah, what were we doing? We were talking about the definition of a Markov chain or Markov process last time, and we did a lot of manipulation with conditional probabilities, the kinds of manipulations we're going to do over and over again in this course. Now, in the last video, I did use independence at least twice, probably more than that. And I didn't talk about any definitions for independence. That falls clearly into the realm of your prereq basic probability course. But I was thinking about it after I edited the last video, and I did want to say a few words. So the usual definition for independence of events A and B is to say that A and B are independent if and only if the probability of the intersection of A and B is the product of the individual probabilities. Now, I always have a really hard time motivating this for students when I do teach like a basic probability course, because I don't find it myself to be very intuitive. The best I can usually come up with is to say that, you see, they separate independent, right? But if I were to think of it only in that way, then you might ask, well, why don't they separate into a sum? Why the product? And so I'd like to take a few moments here before we really get going today to share with you how I like to define independence. And it's going to be equivalent to this usual definition of independence. Now, I like to define independence using conditional probability. So events A and B are independent if. Let's consider the conditional probability that A occurs given that B occurs. If they're independent, the fact that B occurs should have nothing to do with A occurring. This is just the probability that A occurs. I think this one makes a lot of sense to me, this way of looking at independence. So this is my favorite way to define independence. And in fact, it's equivalent to your usual definition of independence, because if we break out this left-hand side to be, by definition, the probability of A intersect B over the probability of B, and then equate these two sides and solve for the intersection probability, we will get the product of the two probabilities, and this is the way you usually define independence. So going from here to here always works, but going in the other direction, you could have a problem if the probability that B occurs is 0, because starting with this as your definition of independence, you can't get to this by dividing by a 0. So that's the only place where you could have issues. Otherwise, these are essentially equivalent statements as long as you watch out for dividing by 0. I don't know what you think. I think this, to me, again, is much more intuitive as a definition of independence. Let me know what you think in the comments below, but let's get back into it. So suppose that I have a sequence of random variables, a stochastic process, a capital X0, capital X1, capital X2, etc. We said last time that we would write this down by putting a capital Xn in brackets. And then on the brackets here, I indicate that n is going from 0 to infinity. So suppose this is a Markov chain, meaning it has that Markov process. I'll remind you of what that is on a discrete state space. So time here, discrete, states, discrete. And I'm going to stop saying this really soon because we're going to be talking about discrete time and discrete states for maybe up to half of this course, maybe even a little more. So I'm going to stop saying this shortly, and you should assume that everything is discrete until I let you know that things are actually changing. So the definition of a Markov chain or Markov process is that this process has to have the Markov property, which looks like this. So this says the probability that xn plus 1 equals some j, given the entire past history of the chain, is just the probability that xn plus 1 equals j, given the previous time step value. This was our definition, and indeed a lot of people's definitions, and there's a little more here I should say. This has to hold for all n and for all states, little I0, little I1, and all states in the state space. And we did last time talk about how this has to hold as long as the conditional probability is defined on both sides of this equality, because if it's not defined, that doesn't mean you don't have a Markov chain. It means this is not one of the probability statements you should be looking at. It's not if it's not even defined. So the new thing for today is I wanted to let you know that missing values are okay. The Markov property really is just telling us to use the most current piece of information, not necessarily the previous piece of information. The easiest way to do this without having a lot of subscripts and symbols is just with an example. So, for example, the probability that x4 equals 2 given that x2 equals 5 and x0 equals 0. You can see that I'm missing time steps x3 and x1, but the Markov property actually tells us that this is equivalent or equal to the conditional probability that x4 equals 2 given that x2 equals 5. I'm going to show you today that we get this from our definition. In fact, some people use a definition to begin with that is more general than the one I wrote down, which would already include cases like this. But I'm going to stick with my definition from the previous video and just show you that we get this from the Markov property. Now, I'm going to hold the proof to the end of the video, actually after the outro, if you want to see it. I do think it's important to see. I really think it's important if you want to study Markov processes to understand how to prove this. And you might just try to prove it on your own and see if you can convince yourself and not even watch my proof. The reason I'm putting it off is because the calculations are a little bit tedious. I think they're fun. I'm not trying to avoid it, but I think it will kind of slow our motivation to get going today, to get bogged down in these sorts of weeds. So I'd like to talk about some other things first while we're still feeling fresh, and then come back around to this at the end. So, fresh feeling people, I have a thing for you. Suppose that xn in brackets is a Markov chain. And by the Markov property, we know, for example, that the probability that x2 equals 1 given x1 equals 0 and x0 equals 5 is just the probability that x2 is 1 given that x1 is 0. I have a question for you. Does this mean that the random variables x2 and x0 are independent? The answer is no, because even though I got to drop x0, and I did just talk about how I like to define independence with conditional probability, the random variable x2 depends on the value of x1, and x1 depends on the value of x0. So really, x2 does depend on the value of x0. But what we can say by this kind of statement, given the, I don't know if it's new to you, but the new definition of independence is that x2 and x0 are conditionally independent, given that x1 is 0. So they are independent in the conditional universe where x1 equals 0, or really where x1 equals anything. So again, x2 depends on x1, depends on x0. So yes, x2 depends on x0. But once the value of x1 is fixed, then x2 no longer depends on the value of x0. So we call this conditional independence. Now let's revisit our green ball, white ball example from the previous video. I had 2 urns labeled 1 and 2. I had a total of 6 balls, 4 of which were white and 2 of which were green. And they were put into 2 urns in some way that each urn contained 3 balls. And xn, our Markov chain, is going to follow the number of green balls in urn 1 as we start a process, and that process is to randomly select a ball from each urn and switch them. Now, xn can take on values 0, 1, or 2 because we don't have a total of 3 green balls, so we can never get all 3 balls in urn 1 to be green. We can at most have 0 green balls, 1 green ball, or 2 green balls. So last time we looked at this long conditional probability that at time 7 we had 1 green ball in urn 1, given that at time 6 we had 1 green ball in urn 1, and at time 5, 4, 3, 2, 1 down to 0, we had this whole history. We realized that how the chain is changing values between time steps really doesn't depend on the sort of further back history. So given that at time 6 we have 1 green ball in urn 1, the only way we're going to continue to have 1 green ball after we randomly select 1 from each and flip them is if we grabbed the green and the green at the same time, just basically swapping 2 greens, but not changing the total number of greens in either urn. Or we did the same thing with the whites. We swapped a white and a white, not changing anything about the total number of greens in urn 1 or urn 2. And so we argued that this is a Markov chain and we didn't need this past history. And when we worked this out, we got 5/9. And it's easy to see, given this example, that what we did not depend on the time we were looking at, on the fact that we were starting at time step 6. At any time in this process, if you have one green ball at, say, maybe time 85, the probability of having one green ball at the next time step 86 is still going to be this 5/9. It's still going to be computed in the same way. So this from here to here is the Markov property, but a Markov chain does not have to have this sort of thing holding. It will for almost every Markov chain we look at in this class, and it's known as a time homogeneity property of our Markov chain. So 5/9 is said to be a one-step, meaning one time step, a one-step transition probability in a time homogeneous Markov chain. I will have a couple of examples of chains that are not time homogeneous, but you should assume time homogeneity throughout unless I state otherwise. Let's find another one-step transition probability for this chain. So let's find, for example, the probability that starting with one green ball in urn 1, after we select and switch, we now have 2 green balls in urn 1. This probability is going to be slightly easier to compute than the last one because there's only one way for this to happen. There isn't like a green and a green or a white and a white. If I start with a picture that looks like this, because here's a picture with one green ball in urn 1, the only way to end up with 2 green balls in urn 1, this means I have to pull a white out of this one and a green out of this one and switch them. And the probability I get a white out of this first urn is 2/3, and the probability I get a green out of the second urn is 1/3. So we get 2/9. And here is another one-step transition probability. So the state space is 0, 1, or 2 for the number of green balls. And so we can consider going from 0 green balls to 0 green balls, 0 to 1, 0 to 2, etc. Let's organize these one-step transition probabilities. We don't say it, but again, that's one time step transition probabilities. We can organize these into a one-step transition probability matrix. This is usually denoted by some sort of capital P that's like extra bold because there's lots of P's flying around when you're computing probability. So this is the notation I'm going to use, this kind of double-lined P. You can use something else as long as it's clear to you, and if you're my student, clear to me when I'm grading. But I'm going to make a matrix, and I'm going to put the state space down as the labels for the rows of the matrix and also across the top. And in the matrix, I'm going to put the probabilities we've already computed. So we talked about the probability of going from one green ball to one green ball as being 5/9, and one green ball to 2 green balls as being 2/9. So these labels over here are your from states, and these labels up here are your to states. We can compute the rest of these. By the way, you know what? Let me just compute them. So the rest of the probabilities look like this. And if you want to, pause the video and maybe check 1 or 2 of these to make sure you are getting the right thing. Now, I didn't need to compute all of these because some things are locked in this matrix. If I let lowercase p sub ij be the ijth entry, then this is the probability of going from state I to state j in any one time step. So it might be starting from time 0 to time 1, but by time homogeneity, it might be starting at time n to time n plus 1. And this is going to be the ijth entry of the matrix. Note that if I sum over j, so what does that mean? For a fixed I being one of these indices over here, let's look at I equals 1. Starting with one green ball, in the next step, you can either have 0 green balls or 1 green ball or 2 green ball. And those are all the possibilities. So these have to sum to 1. So that's what I'm saying here in scarier notation. If you sum the lowercase p sub ij over all j, you need to get 1 for every I in the state space. This is, again, just saying that the rows of a transition probability matrix have to sum to 1. The columns do not need to sum to 1. When they do, we have something special going on. I'll talk about that later. But there's nothing like logically about why the columns would need to sum to 1. So make sure your rows sum to 1. And when filling out a matrix, like in a homework problem, you could use this to save yourself some work. But at the very beginning of the course, I might actually compute all the probabilities just to double check. So since we had this 5 nines and 2 nines, I know that this needed to be 2 nines without any extra computation. So I would like to take our Markov chain and answer some questions about it, but I'm kind of sick of this white ball, green ball example, as I'm sure you might be as well. I can't say sure, might, but I think you might be as well. So as another example, we have, and I'm simplifying this model, but we have electric scooters on campus, like you might see in a city, like those Lime scooters or things like that. Now, those could be left anywhere on a sidewalk, but here on campus, if you don't put them back into the racks, you are going to continue to be charged for them. So people take them generally from a station or a rack of scooters to another station. I'm going to call 3 stations here, A, B, and C, and I'm going to assume that scooters move between the stations according to a Markov chain. So there's no, why would that be Markov? Prove that it's Markov. It probably actually isn't. This is just an example for us to get some numbers to work out some probabilities. So I'm going to assume that it's Markov and that no scooters are left on the side of the road, or maybe if they are, eventually someone picks them up and puts them in a station, and maybe that's built into my matrix. It's an example. It's an idealized example. So what is the actual chain here? I'm going to let xn be the station location of just a particular scooter. We're going to pick a scooter and follow it around as it travels around campus between these stations. So I've got some questions for you. Let's find a bunch of probabilities. The first one, quite easy. The probability that x1 equals A given that x0 equals C. Now, before I go any further, I do have to say that random variables are supposed to be numeric. So you shouldn't be able to say equals a symbol like A and a symbol like C, but they are just labels. So if this is bothering you, then redefine the states and call the labels of the stations 1, 2, and 3. I just thought this was a little more clear with less numbers floating around, and I think you know what I mean. So yes, random variables should be numeric, but I'm letting A, B, and C stand in for what would otherwise be numeric labels. Okay, so the probability that x1 equals A given x0 equals C, this is the probability of going from C to A in one time step. So we're going to read this right off of the matrix. We're going to say we're starting at C, that's where we're coming from, and we're going to A, and read this probability right here. The answer is 0.70. So as a second question, what is the probability that x73 equals A given x72 equals C? By time homogeneity, this is the same thing. We're just moving in one step from state C to state A, and again, we get the probability of 0.7. Let's make this only slightly more interesting. My third probability is what is the probability that x73 equals A given x72 equals C and x51 equals B. Now, by the Markov property, I don't care where the scooter was at time 51. I know where it is at time 72. It's at station C, and the probability we move from C to A in one time step is again right here, and it is 0.70. Okay, let's look at part D. What is the probability that at time 1, our scooter is at station B? There is not enough information for us to answer this question because the matrix only gives us transition probabilities. It says, given you're here, this is the probability you'll be in state B at the next time step, but it can't just give us a probability alone like this without conditioning on where we were before. So there's actually not enough information for us to answer this question. What we need is a so-called initial distribution, the probability that our scooter is going to start off at, say, station A, B, or C. So I'm going to totally make something up here and say that suppose that the probability that at time 0, the scooter is at station A is 1/2, and then the probabilities at B or C is 1/4 each. And again, I just made that up. It's part of my example that I'm giving to you to answer questions from. So there's no, how did you get that? I just made it up. But to find this probability that I care about, what we're going to do is condition on where the scooter is at time 0. So I'm going to write this probability that x1 equals B as the probability that x1 is B, given x0 equals A, times the probability that x0 is A, plus the probability that x1 is B, given that at time 0 we're at B, times the probability that at time 0 we're at B. And then the same thing, conditioning on us being at station C at time 0. So these three probabilities I just wrote down for you. They were 1/2, 1/4, and 1/4. And these other probabilities are coming out of the matrix. So the A to B probability, for example, is right here at 0.4. The B to B probability is right here at 0.05. And the C to B probability is right here at 0.2. And when you put these all together, you end up with 0.2625. So again, if you see something like this, you cannot answer this with a transition matrix alone. You need some sort of initial distribution for your Markov chain, the probability that you're starting in one state versus another. Okay, so let's kick this up a notch. Let's look at the probability that x2 equals b given x1 equals a and x0 equals a. The first thing to note is that this is not a conditional probability. And all I know so far, I'm going to assume that that initial distribution I just defined for part D is still holding for the rest of the problem. So the first thing I want to do is rewrite this in terms of conditional probability. This is like an event A, not to be confused with the state A, and the event B. This is like a probability of A intersected with B. And I can write that by unraveling the definition of conditional probability as the probability that A occurs given that B occurs times the probability that B occurs. Again, sorry to reuse those letters, but this joint probability here is the probability that x2 equals b given the other two times the probability of the other two. And I'm going to use that same idea here to rewrite this joint probability as a conditional probability that x1 equals a given x0 equals a times the marginal probability that x0 equals a. So now I know this was my initial probability of 1/2. And then this is the probability of us going from A to A in one time step, which you can read off the matrix. Over here, I could use the Markov property first to get rid of this. And what's left is the probability of going from state A to state B in one time step, which can be read off the matrix. And so we end up with the 0.4 probability of going from A to B times the A to A probability of 0.10 times the initial probability of being in state A, which was 1/2, and we get 0.02. So this is the game to play when answering questions about a Markov chain. You're likely going to need an initial distribution and the matrix, and then you can manipulate all sorts of probabilities into conditional probabilities until you get down to those one-step transitions. As a final question within this example, let's look at the probability that x2 equals b given x0 equals a. So this is not one time step. This is known as a two-step transition probability. We're going 2 time steps. And you cannot read these numbers off of this matrix because it's filled with one time step transition probabilities. So what we can do is we have multiple approaches, but I think given what we know right now, what we can do is condition on the value of x1, all while staying in the universe where x0 equals a. That's already that given information, like from day one of this course. I already know that I've got a face card in my hand. All the calculations should be done within that conditional universe. So let's do it. I'm going to write this as the probability that x2 is b given x1 equals a. And I'm going to keep the x0 equals a on the right side of that conditional line, and then multiply by the probability that x1 equals a in that conditional universe that says that x0 equals a. And I'm going to keep doing this for all the values of x1 till we get something that looks like this. Now, if you are not comfortable yet with conditioning like this, what I would do instead is I would just up here, I would stick in like comma x1 equals I, and then I would sum over I equals A, B, and C. And that joint probability that x2 equals B and x1 equals I in the conditional universe where x0 equals a, when you sum over all the I, brings you back to this marginal probability in the conditional universe. And then you end up doing the same thing I'm doing down here. You just would have given that sort of intermediate step of putting x1 in on the left side of the conditional line. So let's use the Markov property to knock all these out over here. Looking at probabilities for x2, if I know the value at time 1, then I don't need the value at time 0 anymore. And what I'm left with is a one-step transition probability right here from A to B, a one-step here from A to A, etc. and I get these numbers, stop and pause the video and make sure you see where all these numbers come from. But in the end, I get 0.16. So we computed our first two-step transition probability, and we did it by conditioning on where we were at time 1. Let's look a little more closely at this answer and the matrix. Does this look like anything to you based on this matrix? I can see this 0.4, this 0.05, and this 0.2 coming out of this second column, the B column of this matrix. And I can see these other numbers, 0.1, 0.4, and 0.5, coming out of the A row of the matrix. So we ran down a column and we ran across a row and we multiplied values and added them up. This looks an awful lot like matrix multiplication. In fact, the probability of going from A to B in 2 time steps is going to be, and we're about to prove this, I don't want you to believe that just based on this one calculation, but this is going to be the A to B entry of the square of this matrix, of the probability transition matrix or transition probability matrix squared. So we're about to prove this, but this is going to make your life a lot easier if you know this, because while what we did not take a whole lot of work in computing this probability on the previous slide, could you imagine if the number of time steps were really far apart and if there were a lot of values, like a huge state space, maybe even an infinite state space? I wouldn't want to condition on, say, maybe if I had to find the probability that x at time 200 equals b, given that x at time 0 equals a, I wouldn't want to condition on the values at time x1 through x199 and run over, thousands of states. That's ridiculous. So noting that this is matrix multiplication is going to make our lives a lot easier. So before talking about these matrix multiplication shenanigans, I have a little more notation to give you. Let's talk about n-step transition probabilities. That is n time steps for transitioning between a value and another value. I'm going to call lowercase p sub ij and then a super n in parentheses. I'm going to let this denote the probability that xn equals j given that x0 equals I. Or by time homogeneity, this would be the same thing as the probability that xk plus n equals j given xk equals I. Now, this is going to hold for n equals 0, 1, 2 on up, and for k equals 0, 1, 2 on up. And I just want to point out that some books and some resources will not put parentheses around this n. And I'm really not a fan of that because this is our symbol for the probability of going from I to j in n steps. And this is absolutely not the same thing as the probability of going from I to j in 1 step raised to the nth power, which is what it's going to look like if you don't use something like parentheses around this n or a completely different notation. So you may see a p sub ij to the n and it's not a power. And I think that's really confusing. So I'm going to use parentheses around the n just to emphasize. If I just put an n up here, it looks like a power to the nth power, and that's not what's going on here. Okay, so note that pij super 1 in parentheses, if you will, is the probability going from I to j in 1 time step, and we already have notation for this. This is just little p sub ij. And I do have that n could be 0 and k could be 0 up here. Note that it is possible to talk about the probability of going from I to j in 0 time steps. So our new notation is p sub ij super 0 in parentheses. And how do you go anywhere in 0 time steps? You kind of don't, but you can stay where you are. So this probability is going to be 1 as long as j equals I. If j equals I, you can talk about the probability of going from state 3 to state 3 in 0 time steps. Given you're at state 3, the probability you're at state 3 in 0 time steps is always 1. And the probability you move somewhere else is always 0. So this is going to be something important for us to kind of wrap up calculations cleanly when we start to have sums and double sums floating around and you suddenly end up with a super 0. All that's happening here is you're getting this kind of delta function kind of thing, or like an indicator that you stayed where you are in 0 time steps. With our new notation, we can now talk about the Chapman-Kolmogorov equations. It's going to be abbreviated as we go forward as the CK equations. And I'm going to start with a Markov chain on a discrete state space in discrete time. There are versions of Chapman-Kolmogorov for other situations. We'll talk about that when we get there. But there are a couple ways to write this down. My favorite way to write this down is to say that the probability of going from I to j in n plus m time steps is, and what we're going to do is look at going from time 0 to time n plus m and sort of cutting that journey into the first m steps and the remaining n steps. And so after the first m steps, you are somewhere. And then you go from that somewhere back to j. So you start at I, and after m time steps, you are somewhere. And then in the remaining n steps, you go from somewhere back to j. But the particular somewhere is not important. This probability is just the probability you go from I to j in n plus m time steps. So we're going to sum over all of the possible somewheres. This is the probability you go from I to some k in m steps, and then you go from k to j in n steps, summed over all possibilities for k. It's like we're conditioning on where we are at time m, and that's, in fact, exactly how we're going to prove this. But first, I want to give you another version of Chapman-Kolmogorov. An equivalent version of this looks like this. So this represents the probability I go from I to j in n steps, and then I'm going to break that up into just the first m steps, where m is something less than n. And I'm going to say I go from I to some k in m steps, and I'm going to run over all possibilities for k in the state space, and then multiply by the probability I finish the journey from k to j in the remaining n minus m steps. So if you look at it this way, you do need to make sure that your m is between 0 and n. And fortunately, we just defined what you would get with these probabilities when the superscript is 0. So you don't have to freak out if you get a 0 up there, because you can go from a state to another state in 0 time steps as long as the states are the same. I'm going to prove the first version of this. They are equivalent. You could adapt my proof for the second version, but let's just go for the first version. What is the probability I go from I to j in n plus m steps? I'm going to write this as, I'm not going to assume I'm starting from 0, but I am in a second by time homogeneity. In its most general sense, this is like the probability given you start at time k at state I, the probability that at time k plus n plus m, you're in state j. But again, by time homogeneity, we might as well start from time 0. That certainly looks a lot nicer. Now I'm going to condition on where the chain is at time m, and you know how to do this. You can just, maybe it's too soon. I should have done more examples. I've done this twice now where I've gone straight to this conditional statement. But looking back up here, I can put in a comma x sub m equals k, turning this into a joint probability in the conditional universe where x0 equals I, and summing over all k in the state space. And then I can manipulate that joint probability, unraveling the definition of conditional probability to turn that into this, all while staying in the conditional universe where x0 equals I. But now we're done. By the Markov property, I get to knock off this x0 equals I because I know the value of the chain at a later time step at time m. And the remaining conditional probability sitting here is the probability of going from k to j in n time steps. And our notation for that is p sub kj super n in parentheses. And over here, this is the probability of going from I to k in m time steps. And our notation for that is p sub ik super m in parentheses. And this is exactly what we wanted. I mean, it's written backwards, but this is exactly what we were trying to show. We have proven the first version of the Chapman-Kolmogorov equations. If you want to prove the second version, it's totally equivalent. I don't think we need to do a second proof, but give it a try and let me know if you're having any trouble showing the second version of the Chapman-Kolmogorov equations. Okay, so now let's define an n-step transition probability matrix. I'm going to use this double line bold P super n in parentheses to denote the matrix of n-step transition probabilities. So the ijth entry here is going to be lowercase p sub ij super n in parentheses, not the power of n. We have one version of the Chapman-Kolmogorov equation look like this. And if you look in here, as k is running over the whole state space, because k is changing in this sum, this pik super m in parentheses is running across the ith row of the transition matrix of m-step transition probabilities. And similarly, this pkj, as k is moving over the whole state space, is running down the jth column of the matrix bold P super n in parentheses. So when you go across a row of one matrix and down a column of another matrix and multiply the corresponding entries together and add them up, that is matrix multiplication. This Chapman-Kolmogorov equation is telling us that the matrix bold P super n plus m is equal to bold P super m times bold P super n. Okay, so in the proof of Chapman-Kolmogorov, I conditioned on where the chain was, the value of the chain at time m, and then we looked at the rest of the time steps. But I could have easily conditioned on where the chain was at time n. So my Chapman-Kolmogorov equation like this could easily have come out like this. And so if you look at this one and say, oh, I'm going across the ith row of this and the jth column of this one basically says that the matrix of n plus m step transition probabilities can be written as the matrix of n step transition probabilities multiplied by the matrix of m step transition probabilities, which is the opposite of what we just had. In other words, the Chapman-Kolmogorov equations are saying both this and this. So we do have a commutative property in multiplying probability transition matrices. So check this out. I'm going to look at the matrix of two-step transition probabilities by the Chapman-Kolmogorov equations. This is one way it can be written is the matrix of one-step transition probabilities times the matrix of one-step transition probabilities. Another option would be the matrix of two-step transition probabilities times the matrix of zero-step transition probabilities. But I'm going to do it this way. And the one-step transition probability matrix, that's our original matrix of just the bold P. And when you multiply bold P, that matrix by itself, you get bold P squared. So in other words, the matrix of two-step transition probabilities is the original matrix squared. Similarly, the matrix of three-step transition probabilities by Chapman-Kolmogorov could be written as the matrix of two-step transition probabilities times the matrix of one-step transition probabilities. But we just saw in the line above that the matrix of two-step transition probabilities is just the original matrix squared. And of course, the matrix of one-step transition probabilities is just the original matrix to the first power. So we get the original one-step transition probability matrix raised to the third power, etc. So in general, the matrix of n-step transition probabilities is the matrix of one-step transition probabilities raised to the nth power. And so this could be how you answer those questions where you are skipping a lot of time steps and you don't want to have to go fill in all the possibilities and sum over those and condition on what could have happened. We could answer the question of moving a scooter from station A to station B in 2 time steps by just squaring the matrix and looking at the A to B entry. Again, in that case, maybe it's not worth squaring the matrix, but it will be worth squaring the matrix when you're looking at many more missing time steps and a much larger state space. Okay, I am out of time. If you stick around after the outro, I will show you that example of the Markov property holding when we had some missing time steps. But if you're leaving for now, I'll just let you know that in the next video, we're going to talk about absorbing states for a Markov chain. These are states that once you hit them, you can never leave. Ooh. So I hope to see you in the next one. But stick around after the outro. Now. You stayed. Okay, so missing values are okay. The Markov property, as I stated it, said where you go at time n plus 1, given the entire past history of the chain, it really just depends on where you were at time n. But you could be missing values in that history. You could be missing values in a lot of places in your Markov property statement. So rather than write this out with generic subscripts and I1, I2, all of that, I thought I would just look at a smaller example. And my example is, what is the probability that x4 equals 2 given x2 equals 5 and x0 equals 0? You can see I'm missing time step 1 and time step 3. But this is just the conditional probability that x4 equals 2 given the most recent piece of information we have, which in this case is x2 equals 5. I wanted to show this. And I think that if you were showing this yourself, you might make different choices than I make. I absolutely hate, I stopped assigning problems like this as a teacher because I hate grading them because everyone does everything different at every step. And so it's really, it's hard to grade. But yeah, so you might not make the choices I'm going to make, but that doesn't mean you wouldn't get to the same place. Okay, so I'm going to start with the left-hand side, and my first move may not be your first move at all. Like, for example, your first move here might be to write out the definition of this conditional probability as a three-way intersection over a two-way intersection. I'm choosing not to do that. I think mine's going to be maybe more efficient, but I can't say by any stretch that it's optimal. So if you find something more efficient proof of this, then I'm sure you did it right. So there's so many ways to go here. But I'm going to say, you know what, if I had the missing values in here, if I had the value of x3 and the value of x1, then I could use our definition of the Markov property kind of directly. So first, let's look at putting in x3. I'm going to say that x3 equals I and then sum out overall I. So this joint probability, when I sum out the I, gives us this marginal probability, all while staying in the conditional universe where x2 is 5 and x0 equals 0. Now, I want to do kind of something similar for x1, but I cannot put x1 equals, say, j in here and sum over all j, because conditional probability just doesn't work that way. The stuff after the conditional line ends up in a denominator, and when you sum fractions, you don't sum the denominators. It just doesn't work that way. So what I can do is put x1 equals j on the left side here and sum out overall j. So this is my attempt of turning this probability into something that contains all of the time steps. But I want to be able to use the Markov property as we know it, so I want to move things around in the right way. I'm going to define this to be event A, and then this part to be event B, and then the comma is and or an intersection. So I've got the probability of like A intersect B in a conditional land, and I want to unravel the definition of conditional probability to say that the probability of A intersect B is the probability of A given B times the probability of B. I'm going to do that with this being my event A and this being my event B, but staying in the conditional universe where x2 equals 5 and x0 equals 0. So I want to make sure after every conditional line, I always have these two guys. Right, so here's my A intersect B, and here's my A given B times my probability of B. And then after every conditional line, I always keep these two values. So this first probability here, this is set up for Markov property. I've got a probability for x4 given the entire past history, so I can start knocking some things off by the Markov property. But before I do that, let's look over here at this guy. This is kind of weird because we have x3 and x1 on the left side. And if I wanted to start to move things around, I could use the same trick of unraveling conditional probability. And I can write this intersection here as the conditional probability of this given this times the probability of this, all while staying in this conditional universe. And that would look like this. And that wouldn't be wrong, but I'm not sure it's going to be that helpful. So I'm not going to do it. What I am going to do is use the Markov property to knock some things off over here. And then note that there is no j left in this first probability. So this entire probability can come outside the j sum. And then I've got the sum over I of that conditional probability times the sum over j of this guy. But if I sum over j, the probability that x3 equals I and x1 equals j in some conditional universe, I'm just summing out the values for x1. So I'm ending up with over here, like marginalizing down to what x3 equals. And so what we end up with is this. So the j stuff is gone entirely. So this is the left-hand side of the statement I'm trying to prove. And I could go further, but I'm a little worried about it because I could do so many things. So what I want to do for a calculation like this is maybe now look at the right-hand side and see if I can come in from that side and try to meet in the middle rather than starting all the way from the left-hand side of the equality I'm trying to show and get all the way to the right-hand side. So let's look at the right-hand side of the equality we are trying to show overall. We want to look at the probability that x4 equals 2 given x2 equals 5. I am going to do the same sort of thing. I want to bring in x0 and x1 and x3 so I can bring them in on the left side of the conditional line as long as I sum them out. And then I can play our unravel the definition of conditional probability game. I can write this is like an event A and this is like an event B. So I can write the probability of A intersected with B is the probability of A given B times the probability of B, all while staying in the conditional universe where x2 equals 5. and we get this. I'm going to pull the same kind of trick I did before. There's a lot of i's and j's and k's to sum over, but if you'll notice in this first probability, I do have all the time steps, so I can use the Markov property to knock some of these out, and what's left is the probability that x4 equals 2 given x3 equals I, and that probability does not depend on j or k, so it can be pulled out of the j and k sum. And what I'm left with is a sum here over I of this conditional probability, and then when the j and k sum moves in over here, I'm going to be marginalizing out this value and this value, leaving me with just the probability that x3 equals I given x2 equals 5. So this is the right-hand side of what we're ultimately looking at, and this is the left-hand side up here. And you can see that it looks really similar, except for I need this to equal this. And the question is, are they the same? And if they are the same, we are done. I don't know if this is the most efficient way to do this, but yeah, I could easily write down 10 different proofs, like making different decisions at every step, more than 10 proofs. And I really didn't want to look for the most optimal one. I tried to keep it more streamlined than some other things, which involved writing out the full definitions of conditional probabilities as joint probabilities over joint probabilities. I don't know what you think about this, but really what's important here, if you're trying to follow along, is not why did you do that, but when I say this line is equal to the next line, could you agree? Could you agree? Could you see why the next line is equal to the previous line, and maybe not have the motivation for why I did that? Okay, so let's look at this guy up here. This is the bringing in x1, which is the only thing missing here, the sum over all j in the state space of the probability. So I'm going to put in x1 equals j right here. And I am going to rewrite this. I'm going to try to move the x1 to the other side. So this is like an A intersected with B in this conditional space, and I'll get the probability that A occurs given B occurs times the probability that B occurs in this conditional space. And then over here, I've got the Markov property, so I can drop some things, and the J sum can move all the way over in here. Like I can pull the conditional probability that x3 equals I given x2 equals 5 outside of the J sum. But look at this. I'm summing over J of the probability that x1 equals J in some conditional universe, but I'm letting J run over the whole state space, and that probability is going to be 1 because x1 has to equal something in this conditional universe where x2 equals 5 and x0 equals 0. So if I run over all values, we're going to get 1. And we end up with just this part, which is what we wanted to show. On the previous slide, I had a circle, and I said, are they the same? This is the first circle, and this is the second circle. So we're done proving that we do get that this side equals this side from the Markov property. And we could do the same sort of proof for a general n values with like an I0 and I1 and I2, but it gets really messy because you can see it was kind of tedious and messy even in this finite small time step case. But the idea is the same. So missing values are okay for a Markov chain. If you have a conditional probability like this, I might not have the previous time step for this. So x4 equals 2. I don't have what x3 is, but you can just use the most recent piece of history and call it the Markov property. Okay, so we're done. Hope to see you in the next one.